All right, your exams are not graded, but I do hope to have them ready later today. Again, that's a hope, not a guarantee. I am so ready for the semester to be over, having taken on this extra load, but if I get these exams done, for me, I've done the hardest part for the semester. So, now we can talk about the final exam today, or we can talk about it Friday. Today, Friday. Today? Today? Then you get to think about it a little longer? Okay, so final exam, you have a handout there. If you open up and look at that final exam guide, this gives you some details about how you prepare for the ACS standardized final exam. And ACS stands for the American Chemical Society, which is the largest professional organization in the world. Been around for over 100 years. Anyhow, I've taken a lot of these as a student. These ACS exams have been around like forever and ever and ever. And it's a test that you take basically where your score on the exam is based on your performance relative to the national norms that have been prepared based on other students that have taken that exam before. And there's results from thousands and thousands and thousands and thousands of students. So again, your grade's going to be based on your performance relative to those national norms. Probably the number one thing on this exam is that programmable calculators are not allowed. And I know that for some of you, your only calculator is like your TI-84. I do have a whole bunch of these types of calculators, ones that you can use. There's some that are available like this down in the library that you can check out. However, I would ask that if you're going to go down and try them out, that you try them out this week. So next week I can go down there and check out a whole set that I can share with all my class and my colleagues can. So if you want to try it out this week. They'll check it out just so you can just check to see where the buttons are or whatever. And heck, for all I know, if somebody finds a TI-30X2S simulator online, you can probably practice one online just so you know how they work. But again, only non-programmable calculators are allowed. If I bring in some calculators, how many am I going to need? How many do not have access to a non-programmable? Raise your hands high so I have an accurate count. 2, 3, 4, 5, 6, 7. Okay, I easily have 7 calculators that I can provide, and I'll have a couple extras with just in case those that aren't here need one. Now, as far as where next week goes, that is not the right time for a final, is it? I don't think so. I copied and pasted a page and then forgot to update the time. So our final exam in here, when you look at our syllabus, I believe it's Wednesday at 7:30. So we'll check here real quick. We're 1061. Course syllabus. It's probably on your calendar. There it is. All right. Wednesday at 7:30 a.m. Wednesday, 7:30 a.m. And we are in this room. We are in this room. So Wednesday, 7:30 a.m. For those of you that have not been through finals week here at Anoka Ramsey before, the only thing that goes on during finals week is finals. So there's no regular lecture, no labs or anything. The only meeting that you have, lecture or lab, for finals week next week is going to be for your final exam, and that'll be in here at 7:30 a.m. You will not want to be late for this exam. This is one you will not want to be late for because it's a standardized exam. That means it has a very defined start time and a very defined end time. You have 110 minutes. If you come in late, you will not get 110 minutes. And it's going to be one like if you've gone and taken the ACT test before, you're going to sit down there with your test. The test is going to have the cover there. You can't peek anywhere else. You're just going to look at that cover. And then once the time starts, you'll start it, and you're going to have 110 minutes from the time I tell you you can start until the time that it ends. Probably the number one thing to know about this one is that your grade is going to be based entirely on the number of questions you have right. So that means if it gets down to the end and you're running out of time, just fill in whatever that you have to make sure that you have at least answered something for each of the questions. There are going to be 770 multiple choice questions on the exam. Again, there's going to be 110 minutes that are available. Now, as far as things that you're expected to know, I'm not going to go through every one of these because I know you know how to read. So you can go through and read these things that are expected of you. A couple things we should note. If you do look at this, for example, you're going to be looking at the polarity of bonds. You look at stuff like what's called the Vesper model, molecular geometries and such. Some of these stuff in here, you'll say, I've never seen that stuff before, and that's because that's things that we're going to be covering here this week. So again, we'll be looking at that stuff. And then if you look at the next bullet point, this one here talks about intermolecular forces, lattice energy, and such. These here are not covered until Chapter 11. And Chapter 11 is not a part of this course. So before you say, well, that's not really fair because I'm going to be graded based on how I perform relative to my peers nationally, what I will say is that relative to your peers nationally, they don't all cover the material the same way we cover it here. It's just a matter of where you wind up going to school. Some places don't cover thermochemistry, for example, until the second semester. And they cover thermochemistry along with thermodynamics, which is chapter 17 or 18 in your text. So it's all covered as one unit. Some don't cover gases until you get up to about chapter 12, one of the first topics in Chem 2. We've already covered that. So again, depending upon where you go, there's always a few different orders. We may not cover everything that's the same. So collectively, on a national basis, everybody's in the same boat when it comes to hey, maybe we haven't looked at this. So again, if you go through this list, you'll see that those are things, basically, if you just go through the table of contents of items that are listed in your textbook. Now, a couple of things I noticed happened here on your printout. One was I saw some equations got cut off. Your density formula is cut off, but of course, that's not one you're going to be provided. That's the one that you need to know anyhow. And then the one for the combined gas law, the P1V1 over T1 equals P2V2 over T2. For some reason, I see that one got cut off as well. So these equations that are in here, that doesn't mean that these are provided for you. This means that these are ones that you should know. And before you start worrying too much about these are ones you should know, these are things, most of these ones that you're expected to know are ones that you should think of based on common sense. For example, if we talk about the density, you know the density is defined as being the mass per unit of volume. You don't need the formula because if you know it's mass per unit of volume, the word per mathematically means to divide. So again, if you think about them, and then if you think about the various gas laws, just think about pressure and volume. As one goes up, the other one goes down. When it comes to volume and temperature, as one goes up, so does the other. So if you think about those relations, and if you need to, Pivner, think of some ways to think of shortcuts to learn them. This one here is the law of conservation of energy. Whatever energy is lost by the system must have been gained by the surroundings. So again, as you think of these equations, don't think about them memorizing them as variables. Think about them based on the concepts, and you'll be fine with them. Probably the biggest place where things will look maybe a little foreign to you is that an international convention for labeling of units is used in here. That international convention does not write units with numerators and denominators. For example, you will not see something written as meters per second like this, but rather you'll see it written as meters dot seconds to the negative first. So this is the way that you will wind up seeing units on your ACS exam. Something like this. We talked about the gas constant, which is in liter atmospheres per mole dot K. Instead of seeing it written like this, help me out here. This would be written as liter atmospheres. Right. So again, this is the way that you'll wind up seeing these units on the exam. So just keep that in mind when you look at the units. The international convention is to write them all on a single line like this. As far as what's provided for you, there's a list of abbreviations and symbols that are used, values of numerous constants that you've used throughout the course. It's going to be very similar to the list of constants and such that you've seen on the flip side of the periodic table throughout the semester. And likewise, you're going to see a periodic table just like the ones you received in class. Similar to the one up there, it's going to be the very basic information with the atomic number, the chemical symbol, and the atomic mass. You are not to write an exam booklet. Blah, blah, blah. Read through that. You can do all that yourself, you're big boys and girls. Strategies. Don't let yourself get stuck on a single problem. Remember that your grade in here is based on the number of questions you have right. If you feel yourself getting stuck right away, just move on and leave it till the very end. One of the things that I often found helpful myself when I take these tests is just to write down all my answers onto scratch paper and then transfer them over. So if you leave a spot or whatever, you don't actually start marking and filling in the wrong bubbles or anything else like that. As far as a studying strategy goes, I took these all the way through college. There's a ACS exam for the second semester. There's a full year general chemistry exam. There's an exam for analytical chemistry, one for organic chemistry, one for physical chemistry, and so forth. Now, I always felt like if I didn't know it now, I'm not ever going to know it. And so, I felt like I never really studied a lot for an ACS exam. However, I would not necessarily recommend that as a great strategy for you, because if you want to kill it, especially if your grade is in trouble right now, or you're sitting at a B and you want to be an A, or if you're at a D and you want to be a C, then you darn well better spend time studying on there, because that's going to be the best way that you are going to prep yourself for it. And again, I would spend the least time studying what you know well and spend the most time studying the things that you don't know well. The cumulative skills problems, the challenge problems, the ones that are near the end of each chapter are the ones that I would recommend practicing the most in your studies. And then finally, as far as how your score is going to be determined, your score is going to be determined based, again, on how you perform relative to the national norms. When you are scored, if you know how percentiles work, for example, if you score, percentiles and percents are not the same thing. If you score in the 57th percentile, what that means is you've scored better than 57% of the other people that have taken the test. And so the way that grades are going to be assigned is like this. If we break it into quintiles, which is 5 different categories, the highest quintile, which means the 80th percentile and above, you will receive an A on the exam. If you're in the second quintile, which is from the 60th percentile to the 79th percentile, you'll receive a B on the exam. If you are in the middle quintile, which is from the 40th to the 59th percentile, you'll receive a C. If you're in the second from the bottom quintile, which is the 20th to the 39th percentile, you'll receive a D. And if you're in the lowest quintile, which is the 0th to 19th percentile, you will receive an F on the exam. So, if we're talking about trying to get an A in here, what is the minimum score you're going to need out of 70 questions? 51, exactly, which means you can miss 19 questions out of 70 and still get an A on this exam. So what that means, it's not designed for you to get 100%. Now, it doesn't look like a lot of you are drinking age in here, but I always say that if you get a perfect score, I'll buy you a beer. And if you're not legal, I'll buy you lunch, all right? Okay? That's because I've never had a perfect score in all the years that I've done this. I've never received one as a student, never had a student that have gotten it. But if you get one, I'm treating, okay? Deal? All right, highest score I've seen in all the years is a 68. So again, these are not designed to get 100%. So basically what you're going to do is like the lowest of the A's is going to be a 51 out of 70, which puts you in the 82nd percentile. 82nd percentile would be like scoring a 91 out of 100. So that's what your scale exam score would be. Because the score is going to be represented out of 200 points, we'll basically take your scaled percentage, multiply it by 2 to get that score out of 100. So, any questions on how the grades are determined on this exam? Any questions? Yes?
Well, this is a little different. How does it affect our final grade for the class?
A point is a point is a point in here. So, each exam that we've done up to now has been worth 100 points. This is worth 200 points. So this is the equivalent of 2 exams. So can it affect your grade? Yes, in a very big way. It can affect your grade, both to the positive and to the negative. What I will say though is that most students have their grades locked in, and by that is that if you've been a C average student, I don't see A's on here, and if you've been an A student average, I don't see many C's from those people in here. So basically how you performed is how you perform on there, but I have seen some where they have influence, but generally if it's been changed, it's been plus or minus 1 grade at the most. Yes?
How do the questions on your exam usually compare to the ACS exams?
Well, my exams are designed for somebody to at least get 100 sometime. Okay, it doesn't mean that you'll say, hell no, I'm never going to get 100 on your exam. Well, people do. Okay, and so that's kind of the difference. So I would say that my exams are a little bit easier than the one that you would see here, but the types of questions, if there's one that you felt like was a challenge, there'll be ones that'll feel like a challenge. You're going to go through some of them and say, I can't believe these are so easy. So they are all multiple choice. That's the one thing, is that they are all multiple choice. So if you go through even your problems where you're doing calculations, rather than seeing the results, one that you have to show your work or whatever, you'll see them as choices on there. Okay, so I don't know, that's an evasive answer, but it's the best I can do. Anybody else? Not intentionally evasive, it's just the truth. Okay, anybody else? Yes?
Will there really be Lewis dot structures on it then?
There will really be Lewis dot structures on there, except you're not going to draw them out, you're going to see which ones, okay. Right? And probably the toughest thing is we're going to start talking about molecular geometries today. We're going to be looking at stuff on 2-dimensional paper that exists in 3 dimensions. And that was, honestly, the stuff we're going through right now, when I was a student, was some of the stuff that I had the most difficulty with, because I'm a horrible artist and I can't hardly imagine 3 dimensions. Okay, so it's the 3-dimensional stuff that you put in 2 dimensions that always gave me the most trouble. Anybody else? All right, so today we are going to talk about some molecular geometries. I did bring out some molecular model kits. If anybody wishes to have a model near you, you can feel free. I will put these over here so you don't feel like you have to walk all the way up. Anybody just want one? All right. And let's just try not to put more. Does anybody else want one here? Spread them out. Yeah. Anybody else? Okay. Okay. So today we are going to look at begin our look at molecular geometries, and in one of the handouts here you have a page that looks something like this right here. We're going to go ahead and complete this page today. We probably won't get on to the next page here until class on Wednesday. But today what we're going to be looking at is what we call the valence shell, electron pair repulsion model. The valence shell electron pair repulsion model. And we take the first letter out of each one of these, and for short we call it the Vesper model. Even though it's not spelled that way, we call it the Vesper model. Now what the Vesper model does is this. First of all, it helps us describe why molecules are built the way they are. Help tell us why molecules are built the way they are. And basically what they depend on is how the electrons are arranged in the valence shell, which is where? The outer shell. And then it's the behavior of the electron pairs that are in the valence shell. And of course, if they have light charges are going to repel each other. So if they repel each other, what they want is they want to take up as much space from each other in 3 dimensions. So what I'm going to do here today is I'm going to take these balloons that some of you blew up here for me, and these balloons are going to represent pairs of electrons. And I selected balloons because what I'm going to do is I'm going to start tying these balloons together, and as I tie them together, they're going to want to push apart from each other, just like the electrons are going to push apart from each other in the valence shell. And so we want to imagine each pair of electrons as a pair of electrons, or each balloon as a pair of electrons. And so in 3 dimensions, if we had 2 pairs of electrons, in 3 dimensions we can't get them any further apart than this. And we would say that this arrangement is one that is linear. And so what you're going to imagine now is that where I have them tied together here, these represent the nucleus. And these here then are the orbitals. So in 3 dimensions, we say that the orientation that places them as far apart from each other is described as being linear. And we have 2 groups of electrons. Again, it's linear. And if you have the model kits, what I placed out there then, I've pre-built these for you. There's one that looks like this. This one should be the simplest of all of them. What is this angle right here? 180. Exactly. So I'm going to use a generic chemical symbol of X, and then I'm going to show the pairs of electrons like this. And so when we have 2 pairs of electrons in 3-dimensional space, the farthest apart that 2 pairs of electrons can be is at an angle of 180 degrees. So next we are going to go on and look at 3 groups of electrons. Remember, now we're looking at electron pairs. So what I'm going to do here is I'm going to tie in a 3rd pair, and we are going to envision these balloons as representing those electron pairs. In 3 dimensions, they are going to push each other apart from each other as far as possible. And in 3 dimensions now, if we look at this, you'll see that the arrangement looks a whole lot like this one right here. So you see all of the balloons sit on the same plane. Again, I have it sitting out there in the kits. So they all sit on the same plane. And if we look at this, the angle that's in here is 120, because in a circle we have 360 degrees. So the name that we give to this here is called trigonal planar. It's kind of like the shape of a triangle, so it's trigonal planar. And then if we were to represent this, we'll put a generic symbol X in the center, and then we'll show the pairs of electrons. And by the way, now when I'm writing these dashes, that's simply just to show that the pairs are, these aren't an extra pair of electrons. These are just showing that I'm drawing a line basically out to the pair of electrons so we can see what those angles are. then the angles that we find in this arrangement is going to be 120 degrees. So now if I tie in a fourth pair here, looks like my third one just came undone, so we'll tie in another one here. And now if you're looking at these, you're going to pull out the one that has 4 sticks attached to it. I don't know why I can't get these tied today. I'll try one more. Move this around. Try that one in here. See if that'll work. There we go. So now in 3 dimensions, if I have 4 pairs of electrons, this is how 4 pairs would look. Now if I stand this up, you're going to notice that I can stand this up several different ways. I can stand it like this, like this, like this. No matter how I stand it, it basically looks like a tripod with 1 balloon sticking on the top. So again, tripod with 1 balloon sticking on the top. And that would be this one right here. Because no matter how I put this, again, it's going to look like a tripod with 1 sticking on the top. And so I can turn this a whole bunch of other ways, and it looks the same way. So now, to get the name for this shape here, what we're going to do is we're going to put in imaginary lines between each of these vertices. So again, imaginary lines between each of these vertices. If I start drawing it in, I'm going to wind up with a 4-sided object, each side of which has a face that is the shape of a triangle. And specifically, what type of triangle? Equilateral triangle. Exactly, it's going to be an equilateral triangle. And so if we have a 4-sided object, what do we call a 4-sided polyhedron? Not a pyramid. Tetrahedron. Tetrahedron, exactly. It's called a tetrahedron. Called a tetrahedron. So we describe this geometry here as being a tetrahedral geometry. Tetrahedral. And we get tetrahedral when we have 4 groups around the central atom. And in 3 dimensions, we cannot get these balloons any further apart from each other than this tetrahedral arrangement. Now, anybody happen to know what the angles are in a tetrahedron? This isn't one you're going to normally learn. These angles in here are going to be 109.5 degrees. 109.5. Do we need to memorize that? The answer to that question is, yeah, we do. So, now to draw this, now here's where we try to help the non-artist like myself. The way you're going to look at it like this now is you're going to see that these two here are on the same plane. So you'll kind of envision this as being the plane represented by your paper or on the screen. And so we want to draw them on the same plane. So we're going to show a pair of electrons going up on this plane. And let's see, we want to show it to the left. So we're going to put a pair here. Then if we look, you're going to have one pair that is projected outward from the paper or the screen, and one that's projected back into the paper or the screen. To show one that is projected outward, we show a wedge. So again, a wedge shows it being projected outward like this, and then we use a dotted line to represent it being projected back into the paper or the screen. So here's how we show the structure 3-dimensionally, and that's how you'll see it come exam time as well. And once again, these angles in here wind up being 109.5 degrees. So now it starts getting a little bit more crowded. If we get into 5 groups and 6 groups and want to look at those structures, here's how they look. I'll take one more balloon, and hopefully now I've done a good job of tying these in here tight so they don't come apart. And we'll add this around here. Oh, there we go. When they kind of arrange themselves in 3 dimensions now, notice how these two lie to each other, the ones I'm holding on to. What angle are these two here? 180. Then if you look at the ones here that are in the center, it appears that they are in the shape of a triangle. Okay, so it's kind of like combining this one here with this one here. So if we put them all together on one axis, you should have one of them in those kits if you have them that looks like this. It has these two here, which again are at an angle of 180 to each other, which means this angle is how much? 90. And all of these angles in here would be how much? 120, exactly. Now again, to come up with a shape, if we were to go ahead and draw in imaginary lines between each of these vertices, basically if I take this off of here now, I heard somebody mention this name earlier. If we looked at just this piece right here, this would be the shape of a pyramid. And we'd actually call it a trigonal pyramid. A trigonal pyramid because it has a 3-sided base. And so if we turn it upside down, we have another pyramid here. So the name that we give to it is this. It's trigonal bipyramidal. Trigonal bipyramidal, which basically is like a trigonal bipyramid. So now, if we want to represent these angles, here's how we wind up doing it. Remember now we're going to learn we're going to apply what we just learned. We're going to put a generic symbol X in the center. All 3 of these now are going to be on the same plane. So I'm showing this here coming out to your left. So again, showing this coming out to the left. So all 3 of these are on the same plane. So if we want to show all 3 of these on the same plane, we simply draw in the lines like this. You see it's kind of like a sideways T. Then we want to show one of them that's projected out here on your right. So projection outward is going to be represented with a wedge. And there's going to be one that's projected back into the paper, which is going to be represented with a dotted line. So we'll project outward with a wedge, and we project back into the paper with a dotted line. And then when we come up with the angles, this angle here again is how much? 90 degrees. And all of these that are here on this plane sit at an angle of 120 degrees to each other. And so when we have 5 groups in 3 dimensions, we can't get them any further apart from each other than this trigonal bipyramid. Then if we throw in the 6th one, now again things are getting more and more crowded in here. So we'll try to get it in and put these around here a bit. Trying to find something to tie on to. Here we go. Got one to tie on here. And now if I bring this around, tie it in, shake it up a bit, let them come to rest, then what you're going to see in 3 dimensions, these here sit at what angle to each other that I'm holding on to? These are at 180. These are at 180, and these are at 180. So basically then when you look at it in 3 dimensions, this should look like an X, Y, and Z axis. And so in 3 dimensions, looks like this. You're going to have your X, Y, and Z axis. And all of the angles here now, if you look at them, are how much? They're going to be 90 degrees to each other. So now when we draw this, the way that the convention we use to draw, oh, and the name we have for this, if now you all of a sudden start connecting all of these vertices together with imaginary lines, how many faces are we going to have on this object? There's going to be 8, exactly. There'll be 1, 2, 3, 4, 5, 6, 7, 8. And so an 8-sided polyhedron is called an octahedron. So we describe its geometry as being octahedral. And the way that we represent this is we show a generic letter X to represent a central atom. We'll show one above and below. Now we want to show one here that is being projected out on your left and one to the right. So these ones projected out would be represented with wedges, and these two projected back into the paper would be represented with dotted lines. So again, we project one out here and one out here, and we project one back into the paper here and here. And in this one now we can say that all angles are 90 degrees. All angles 90 degrees. Okay, so now what we've just generated here is what we refer to as electron geometries. And we describe the electron geometry like this. We describe it as being the geometry of the electron groups around the central atom. Whether they are lone pairs or bonding groups. And a bonding group would consist of either a single bond, double bond, or triple bond. So again, the electron geometry is the geometry of the electron groups around the central atom, whether they are lone pairs or bonding groups. Now this is just the start. In the end, it's not so much the electron geometry that's going to be important on dictating behavior, but what's going to be most important is what we call the molecular geometry. It's the molecular geometry that ultimately dictates how molecules behave and interact with each other. And we describe the molecular geometry as being the arrangement of the atoms in the molecule or polyatomic ion. So even though it's not really the best term for polyatomic ion, we still talk about what is the molecular geometry of the polyatomic ion. Now, to give an example, we're going to start by looking at something like water, H2O, and look at what the shape of a water molecule looks like. Now, we already told you shape of a water molecule is bent. And so if we were to draw its structure, we come back and we calculate the number of valence electrons. Of course, something like hydrogen is going to have 1 valence electron. Each oxygen is going to have 2 valence electrons. If we come back and draw this out, we have 2 from the hydrogens, 6 from the oxygen. We need 8 altogether. We put in the oxygen with each of the bonds to the hydrogens, which uses up 4 of them and leaves us with 4, which we then place on the oxygen as lone pairs. And so this is the structure we get. And up to now we've said that a water molecule is simply bent without really explaining it. We said that it's not linear. It isn't this one right here. So we want to know then, why is it bent and why is it not linear? Now to describe this, you go back to its shape in 3 dimensions and we look at the electron pair arrangement. And if you look at something like water, how many pairs, that is, how many electron groups do we have around this oxygen? There's going to be 4 in there. 2 of them are used up as bonding pairs. 2 of them are used up as lone pairs. Okay? So we put 2 of them in here as bonding pairs, and we have 2 of them here as lone pairs. Well, since these lone pairs still take up space in 3 dimensions and they repel, a molecule of water in 3-dimensional space winds up being one that is bent. So then the next question might ask is, what do you believe this bond angle to be? Well, we come back to our arrangements here. And of course, there's 4 pairs around the central atom. There's 4 pairs around the central atom. What do we think that this bond angle probably ought to be? Probably 109.5. And it turns out it is not 109.5. Now the reason goes back to what we call this theory in the first place. The name of the theory is the valence shell electron pair repulsion model. So that means that the electron pairs are going to repel each other. So then we go back and say, well, sure, we know that. We want to give them as much space as possible. But then you go back and look at the central atom, and then you ask yourselves, which of these pairs, is it going to be these lone pairs, or is it going to be these bonding pairs? Which one is held more closely to the central atom in here? It's going to be the lone pairs. And that's because the lone pairs belong to just the one atom. They just belong to the oxygen. The bonding pairs don't belong just to one atom. They belong to both the oxygen and the hydrogen. Because these here belong to 2 atoms, that means that they're spread out more. These here belong just to one atom, are held more closely. They're held more closely. If you think about magnets that repel each other, if you get them close together, what happens to that amount of repulsions? They increase, okay? And so the repulsions are going to increase because these are held more closely. If the repulsions increase, what that's going to do then is it's going to repel more, and it's going to push this bond angle in a little bit tighter. As a result, the bond angle in here is not 109.5, but it's actually 105 degrees. Now, we might start talking about bond angles, and we're going to have a whole bunch of bond angles we're going to look at. You're not going to memorize the 105 degrees. What you should know is that its bond angle, though, is less than 109.5. So you need to know the 109.5 part, and then you should be able to predict what happens with the bond angle. In this case, we would predict that the bond angle is going to be less than 109.5, and that's because these lone pairs are held simply by the central atom. The lone pairs are held by one atom. As a result, that pulls them in closer. As it pulls them in closer, that's going to increase the repulsions. The repulsions then is going to push this bond angle in a little bit smaller. So in the case of water, again, what you would need to know in terms of bond angle is, and I don't know, now my thing's not working. So let's see if I can come back here and put it in. So if you come back to this bond angle right here, let's try it now. And I don't know why it's not working at all. We'll try my other stylus. And now I can't even find my other stylus here. There we go. Let's see if this one works. When you put in the bond angle into here, There we go. This bond angle that you want to look at is going to be 105 degrees. What you really need to know, though, is again, that it is less than 109.5 degrees. And again, you should then have the explanation as to why that is true as well.
So is the lone pair angle 109.5, or is it all 105?
Well, it can't be, no, they can't be 109.5. These are less than 109.5. That means these are going to be
More than 109.5?
more than 109.5. But usually we don't look at those angles anymore. What's going to be more relevant is going to be the bond angles. And so the bond angle is what we want to actually represent as far as how the molecules behave and interact with each other. And again, those are called the bond angles. Okay, anybody else? All right, when we come in here on Wednesday, we have this table right here. We have like about 2, 3, 4 minutes left. What I'd like for you to do is to go through and complete columns A and B. And we are going to work on columns C and D in here on Wednesday. But in columns A and B, let's write in their Lewis structure. So these are going to be just like you've done on this last exam. Column A, exactly like you did, except we're going to ignore resonance and ignore formal charges. So just come up with the first structure that you can possibly make. And once you make the structure, then count all the electron groups around the central atom and determine its electron geometry. So I'll give you a couple minutes here to kind of write down the ones that you can. At least give you a chance to compare 1 or 2 with a neighbor. And again, on Wednesday, we will resume with columns C and D. Anybody need handouts from today?